Okay, good to go. This is our first note in the grade 12 college prep course. And as you can see from the title, we're talking about terminology. So it's just the words involved with motion, okay, and some basic idea what they mean. And of course, most of this will be familiar to you, probably, but maybe slightly different context. So either you're writing this or you have a copy in front of you. That's entirely up to you how you think you'll sort of retain it the best, okay? I'll leave that to you to decide. Anytime you need to, you can always hit pause on the video so that you can sort of keep up with what I'm doing, okay? Or rewind, of course. So obviously it's up there. The first term of the lesson is uniform motion. And this is a case where you have no acceleration, meaning constant speed or zero speed, it's the same as constant speed, and constant direction, so you're not changing directions. Excuse me. And you'll see that UM is just sort of my short term for short way of saying uniform motion. NUM, non-uniform motion, so there you would have a change. And we're going to study both of those types of motion in the grade 12 course. The term speed, I'm sure from being alive for the last 17 years, you know speed is how fast something's moving. And in physics class, we give speed a symbol. We give kind of all the terms we learn end up with a little symbol so that we can do math with them, okay? And we can make an equation out of them. So the symbols for speed is V, and it has units of meters per second, okay? You know that kilometers per hour or miles per hour, those are all ways of saying speed as well. Just usually we use meters per second in physics class. And actually tomorrow's lesson I'll tell you how to go back and forth between those. So an example of speed would just be Ferd cycling at 10 meters per second. Okay? And there, you've met Ferd. Velocity is how fast something's moving, so it's kind of like speed, but it also takes direction into account. So, and this may not seem like a big deal to start, and over time you kind of understand it a bit better as we move through the lessons, why, like really the difference between speed and velocity, because it is a little bit more than just saying direction as well. But as far as today's concerned, so we have a symbol for velocity as V with an arrow over top. The arrow means the direction, okay? So direction, when something takes into account direction, you put an arrow over top from a symbol point of view, communication point of view. And that means it's what we call a vector, okay? And we'll talk about vectors shortly. Units for velocity are the same for speed. So the example of a velocity would be Ferd cycling 10 meters per second. And so square brackets mean direction and W means west, okay? So scalars and vectors. So I used the term vector earlier, and we'll talk about that in a sec. First, I'll start with a scalar. A scalar is any, say I use the word quantity, because a quantity is a number, right? A quantity, a scalar quantity, it's something that can have a number with it, but it would not have a direction. So the easiest example is mass. 10 pounds. It would never say I'm 10 pounds east. It doesn't make any sense. Speed, you could say 30 kilometers per hour east, but then it would be velocity. So velocity is set up special to take into account speed with direction. Speed, if you're just talking about what, you take a look at your speedometer and it reads 75 kilometers per hour, that's just the speed. You're not really taking the direction. So speed is a scalar, but as we said earlier, velocity is a vector. So a vector is something that includes direction. So any terms that we talk about that have that you can explain with a number, like time, distance, velocity, all these things, it's either going to be a scalar or a vector, direction or no direction. So when describing velocity, like it usually has a direction with it. Again, we'll talk about why that sometimes isn't the case another day. From a communication point of view, you distinguish between speed and velocity. I know what you're talking about because if you're talking about velocity, you put an arrow over top. Okay? Another one, by the way, that's a vector. An object is located 10 meters north of the car. So I could say that as a scalar by saying an object is located 10 meters away from the car, where it doesn't matter how, which direction it is away from the car, but it only matters sort of that it's that distance away. But if I'm including the fact that it's 10 meters north, I'm making more specific. I'm taking that and making it a vector instead of a scalar. So a scalar would be 10 meters away. A vector would be 10 meters north of the car. Oh, this video. Okay, I can't show this video in my video because of YouTube, but I have it linked on the Schoology, so you should take a look on speed and velocity. It's like 2 minutes. It'll be the best 2 minutes of your day, guaranteed. Okay, some other terms that we're going to talk about today. Position, and it's where something is located compared to something else. So the example I gave last slide, was 10 meters north of the car. That's the object's position. In this one, I'm standing 5 meters west of the classroom door. And because position includes the west, it's kind of more specific than 5 meters away from the door. Because I'm being specific by including west, it's a vector. So position is a vector. And it has a symbol D, which you might say doesn't make any sense. It makes no more sense than calling speed V. And it has the arrow over top. Distance is another one. Another term, completely separate. So it's how far an object has traveled. So I'm driving to London to go see my mom, and I travel 60 kilometers. And I'm not being specific on the direction, right? I'm just saying it's 60 kilometers is how far I went in my car. That's sort of what, if you read, it's your odometer on your car, right? That measures the kilometers that you drive. Just look at that. It says 60 kilometers. It means nothing. I could have turned around in circles a few times. It doesn't matter. It's just how far I went, okay? And it's a scalar because we don't care about direction. Okay, displacement is maybe the most important of the three from our point of view. So it's the difference between start and finish positions. So Ferd walks 50 meters east, then stops and walks 20 meters west. So overall his displacement is 30 meters east. And so, oh, I screwed that up. It's not scalar. Anyway, so let's just look at his walk here. He walks 50 meters east. So we're saying east is in the right direction. So he walks 50 meters east. He turns around, walks 20 meters west. So his displacement is the difference between where he started and where he finished. So he started here, he finished here, so he finished 30 meters east of where he started. And that makes it a vector. That was really dumb. Okay, so displacement, displacement, because it's like another way of looking at it, it's the difference between start and finish. It's like the change in position. And change in, you may or may not remember, the Greek letter that represents that is the triangle. So it's like delta D. So displacement is delta D is 30 meters east, okay, because he finished 30 meters east of where he started. His distance that he traveled, if I was going to ask you his distance, like traveling to London here, he traveled 70 meters, right? He walked 50 plus 20. That's how far he traveled. But his displacement is 30 meters east of where he started. Okay, so here's an equation for us. You can write these down, or maybe you already have it in front of you. When you're doing equations, so you can see the speed and the velocity, pretty much the same, right? Velocity, one way of saying it is rate of change of position, but you could just say it's displacement. This is displacement divided by time. Okay, speed is distance divided by time. So it makes a difference. And either way, if you're rearranging, whether these are the scalars or the vectors, that's the rearranged forms. So the important note is there. We're going to learn another day about formulas for non-uniform motion, meaning there's an acceleration. Excuse me. All of these formulas imply a constant velocity, or you assumed constant velocity. So here's my example that we need to be able to solve by the end of today's lesson. So Ferd skateboards downtown. He initially travels 150 meters south before he realizes he dropped a loonie behind him. So he stops, goes back, and 30 meters to where his loonie is. So if that trip, the 150 south, and then going back 30 meters, takes him 75 seconds, we need to find out his distance that he traveled, his displacement, his average velocity, his average speed. Let's see the solution here. So first I'm kind of sketched it out saying that south was down. So if you look at my arrows here, he went 150 south, kind of turned around and went 30 meters north, right, back to where he came from. So first part A asks us for distance, and distance is just his total journey. So his distance is 180 meters, right? He went 150 plus 30, so 180 meters. Displacement, though, is you kind of look at it from the start to the finish. You say, well, he started here, right? He finished here. He finished 120 meters south of where he started. So his displacement is 120 south. So it's all based on where he is compared to where he started at the finish. Okay, that's displacement. Velocity is displacement over time. So you put 120 and divide it by the time is 75 seconds. So you divide those out. 120 divided by 75 is 1.6. The units is meters per second because it's 120 meters. And the time is seconds. Okay. And it's in the south direction because his displacement is south. And then finally, his speed for the trip, or his average speed for the trip, is 2.4 meters per second because you divide distance, which is 180, divided by the 75 seconds. So you can see that velocity and speed can be very different things. And this is his average speed for the trip, right? Because we know that because he went this way and then he stops, he's obviously not traveling 2.4 meters per second the whole time, but that's sort of the average for his trip. And I think that's it. That's it for our lesson today. First lesson of the unit.